Friends, welcome in today's PK technical classes. So the today's discussion topic is MOSFET. The full form of MOSFET is metal oxide semiconductor and field effect transistors. The specialty about this MOSFET is that this is made up of silicon, which is also a semiconductor, and it has insulated gate, the voltage of which determines the conductivity of the device. The ability to change the conductivity with amount of applied voltage can be used for amplify or switch electronics signals. A semiconductor material always used metal insulator semiconductor field effect transistor is also termed as MOSFET, almost synonymous with MOSFET. And we can also discuss about the main advantage of this MOSFET. The main advantage is that it requires almost no input current to the load current, and when compared with the bipolar junction transistor, it is an enhancement mode operation for the MOSFET, where voltage is applied in the terminal of the gate, which depends to increase or decrease the conductivity of the device. Or we can say that this is a voltage control device. In depletion mode, transistor voltage applied at the gate reduces the conductivity. Usually the semiconductor of choice is silicon. Recently some chip manufacturing, mostly notably IBM and Intel, has started using an alloy of silicon and germanium SiGe in MOSFET channels. So now we can see how and which type of substrate. This is P substrate, we can see, and in this P substrate how these layers are been inbuilt and in which process this NMOS and PMOS has been built up. So let us try to design this NMOS and PMOS with the help of our microwind software. Let's open this microwind software. So first of all, we'll go only the open section, and we have got the MOS gate over here. So now I have to select this P plus diffusion over here. So I have select the P plus diffusion likewise, and we have selected it like 36 cross 5 lambda, 36 cross 4 lambda. And now what I have to do, I have to just select the silicon MOS gate over here. So MOS gate has been selected over here, and I have done this MOS gate. Now I have to select the P plus metal contact over here. Likewise I have selected the P plus metal contact, and now I have to what I have to do, I have to provide the supply of the clock over here. Respective clocks I have given over here, and I will name it as like A, and then after this I have to put the clock over here like B, and assign it. After this I have to put a visible node. Here I have taken a visible node, so I have to put a visible node, the name of the visible node as our PMOS output. So we have done all the processes, so let us check what happened. So we have got the PMOS output over here. We can see that how this PMOS output behaves, where the inputs is of A and B, and for different scaling in 5 nano steps scaling, I have got it. In 10 nanoscale I will get this type of structure. For 20 nanoscale I will get this type of structure. For 15 nanoscale I will get this type of structures, and for 100 nanoscale I will get these types of structures, and for 200 nanoscale I will get this type of structures, and for 500 nanoscale I will get these type of structures. So let us come to the initial state, which is 2 nanoscale. So I have got the 2 nanoscale over here, and we can see which type of signal steps are being gone over here. Likewise, this is 5 nanoscale, so we can compare that as per the inputs, the different outputs, when it is going to be rise and it is going to be fall. At that time, this system, the next signal B is been started over here, and we are going the uprise signal of the output for the A input. Likewise, and this is our PMOS output which we have got. And next, if we go to the design process, we can see the initial substrate, which is P substrate, then we'll take N diffusion, then SiO2 trench isolation, thin oxide growth, thin oxide reduction for polysilicon deposit, N plus implant, P plus implant, embodied DRAM, second polysilicon deposit, create contact, metal contact deposit and etch, via hole and fill, metal 2 deposit and etch, via 2 hole and fill, metal 3 deposit and etch, then via 3 hole and fill, metal 4 deposit. Then we can see that via metal 5 deposit and etch, via 5 hole and fill, MEM dielectric, metal 6 deposit and etch, passive oxide deposit, passive etching, end of the process. Likewise, so this is the total 3D process view we can see, and we can also see the 3D diagram which I have designed. So let us see. This is the top view which you are observing, and now this is the front view. You can observe this is the side view, and this is the back view. We can see all these type of views over here. So these are the designs which I have made for this PMOS transistor. So friends, next we'll design for NMOS. Let us make it erase. Then we will select N plus diffusion, as we are desiring to make NMOS. So we have to select. Likewise, and we will select MOS gate. We have also select the MOS gate, and we will take the metal contact as N diffusion metal in both the places, and we'll take inputs as input A in the gate side, and input input B. Likewise, and we'll put visible node at this position, and we will name it as NMOS output. So friends, let us see that what happens. I have made this structure like this, and we have seen that by this structure what will be the outcome, or what will be the output. So the output of the NMOS is likewise for 5 nanoscale. Let us increase the scaling as 10 nanoscale. Again I will increase it as 20 nanoscale. Again I will increase for 50 nanosecond, and we can see different type of outputs, and these uprising signals are giving like 15.6 picoseconds we are getting, and we can see the input A and input B comparing the inputs, both the inputs, and we can see that these outputs are observing likewise. So by changing different type of scales, we'll get different type of outputs. So these are the relevant output which we are getting. So we can see that what we have done in the 3D process. So at the first step, initial step, we have got a P substrate, then we are getting N diffusion. After N diffusion, SiO2 trench isolation, thin oxide growth, thin oxide reduction for this device, polysilicon deposit, N plus implant, P plus implant, embedded DRAM, second polysilicon deposit, create contact, metal deposit and etch via hole and fill, metal 2 deposit and etch via 2 hole and fill, metal 3 deposit and etch via 3 hole and fill, metal 4 deposit and etch via 4 hole and fill, metal 5 deposit and etch via 5 hole and fill, MEM dielectric, metal 6 deposit and etch, passive oxide deposition, passivation, etching, and the end of this process. So these are the whole processes, and by observing the 3D view, this is the side view, this is the top view we are observing now, and we can see also the side views, both side views, and also the back view. This is the back view. So by this observing this different type of views, we have done this transistor NMOS. And thank you friends, today this much for this lecture. Hopefully we will like it. Thank you from PK Technical Classes for giving your valuable time to us.